Okay, we're going to give another combinatorial number theory problem, like the one we gave in class, that follows from the Cuvari-Shosturán theorem. Okay, so we're going to use extremal graph theory to prove something about number theory. What's interesting here, the theorem is interesting, but what's more interesting is the application, converting it to a graph and then applying what we know about graphs to it. Okay, so we need a definition in order to do this. That's the definition of what's something called the sum set, excuse me. So let's fix a set of integers, call it A. The sum set of A, it's just the collection of all sums you can make by taking two elements from A, okay, is a set of all sums of two elements from A, okay, including taking an element and adding it to itself. Again, that doesn't change much, but we'll allow that, okay? And it's denoted as follows. You just take big A plus big A, and when you write two of them here, it just means that I'm going to look at every single possible way of getting A plus A prime, where A and A prime are both elements of the set A, okay? So if I give you the numbers 1, 5, 12, 15, something like that, all the different ways you can add up two of them at a time, allowing for repetition, just two. Collect those up, all the different sums you get, that is the sum set, okay? And actually, it's an important question in additive or combinatorial number theory. If you know something about A, what does the size of the sum set look like? Or sometimes, if you know the size of the sum set, what did it have to tell you about A? Okay, these are very interesting and often quite difficult problems. And the theorem we'll prove today is exactly of that type. Okay, so this is the theorem of Erdős-Newman, I believe from 77. And it'll give a condition on the sum set, which will imply something about the original set A itself. Okay, so given epsilon greater than 0, well, then for n large enough, okay, if A is a set of non-negative integers such that we make a claim about the sum set, such that the sum set, A plus A, contains the following. Okay, this is kind of funny. The sum set, this is written backwards from the notes, it doesn't matter here, but such that the sum set contains all the squares going up to n. Okay, so it contains 1 squared, 2 squared, 3 squared, all the way up to n squared. Right, so all I'm saying is that the sum set contains 1, 4, 9, 16, and so on, all the way up to n squared. So A is a set of non-negative integers such that the sum set contains all of these. Then we know something about the size of A. If I want to make my sum set capture all of these perfect squares in it, A cannot be too small. And that's what this theorem says. It says that A has to be at least as large as n to the 2/3, maybe plus epsilon or minus a little epsilon here. Okay, so it's got to basically be at least n to the 2/3. A little bit smaller than that, okay? Now this theorem is not the best known. The truth is, if you want to get a sum set to contain all of these guys, A actually needs to be even bigger than this. It needs to be almost linear in n, almost n raised to the first power, almost. Okay, but this is what we'll prove here. Like I said, the more interesting part is the proof of this using some graph theory. Okay? All right, so how do we go about proving this? Well, in order to prove it, we want to quickly convert it into a graph problem, okay? So I'm going to build a graph on the vertex set of A, and I'm going to join edges if basically they lead to these types of things here, okay? So how do we do that? So construct a graph G with vertex set A. So the vertices are whatever the elements are that are inside of A there, and we join A prime from A by an edge if A minus A prime, excuse me, A plus A prime is a perfect square. So is a perfect square that's less than or equal to n squared, okay? It might be that you have numbers in A that add up to perfect squares outside this range. I'm only interested in getting 1 squared up to n squared. Okay, so we join these two. If they're added together, gives us n squared. In other words, it's one of these elements that should be represented in this guy here. Okay, so the first very simple observation is that the number of edges in G better be at least n. Okay, why is that? Well, what's the condition we have on the set A? The condition on the set A is that its sumset contains all these squares and maybe a bunch of other things, probably a bunch of other things, but it definitely contains all these things. How did these things occur in the sumset? Well, I was able to find an A and an A prime such that when I added them together, I got a perfect square here, okay? Actually, this is going to allow, in this case here, yeah, I want to avoid A plus A being equal to each other here, so I'm going to actually, I'm going to change this to any two distinct. Okay, it doesn't change much here, but without that, then I have to actually adjust this a little bit here, right? Because if there was A plus A gave me one of these squares here, I would be putting a loop edge, and then that wouldn't actually be an edge in the graph here. Okay, so the number of edges is at least n, because each of these n things are a sum of the form A plus A prime. So I'm putting down edges at least for those guys, plus potentially much, 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 much more. Okay, so now what I want to do is I want to look at two vertices, A and A prime. So here's A and here's A prime, and I want to count up the number of common neighbors that those two vertices have. Okay, so I want to count up the vertices B that are neighbors of both of those. Okay, so count, so for A and A prime fixed, count common neighbors B of both of the two of them, okay? We're going to find out you can't have too many common neighbors, okay? And that's going to lead us to our extremal problem here. So count up the common neighbors B that are of A and A prime. So how do we do that? Well, if B is a common neighbor of these, it's adjacent to A and it's adjacent to A prime. Why would that happen? Because these edges are present. What this means is, so there exists x squared and y squared, or if you like, you can say there exists x and y, such that the following happens. A prime plus b equals some x squared. X squared is at most n, right? That's why do you draw an edge? If the sum of the two endpoints is equal to some kind of square, okay? These are integers, of course. And also, at the same time, a plus b equals some y squared, right? That edge exists because a prime plus b equals x squared. That edge exists because a plus b equals y squared. Okay, and we're actually going to do a little bit of simple arithmetic here. This is kind of cool. If I take this equation and subtract from it this equation, the b's cancel out, and I'm left with, actually I'm going to take the second equation and subtract from it the first. Doesn't really matter. A minus a prime equals y squared minus x squared, right? And we know this is a difference of two squares, so I'm going to rewrite this as x plus y, x minus y. Okay, so what this means, a prime, x, and y, they're all integers. What it means is this quantity, x plus y, and this quantity, x minus y, both divide nicely into a minus a prime. Okay, so x minus y and x plus y both divide a minus a prime. Okay, so these two quantities divide nicely into that quantity. Okay, now observe, where did x and y come from? They came from B here, right? If I had some other vertex here that was adjacent to these two guys, some B prime, and B prime was something other than B, think for a moment here. That'll still give me some x and y, but a different x and y, right? A different collection of x and y's, just because of these sums with B prime here instead. That's a different number if it's different than B, so I should still get a square, otherwise there's no edge. But the quantities are different there. Okay, so what we want to observe is that each B defines a unique x and y. Okay? So it defines a new x and y, and so actually what it defines, therefore, is a new pair of divisors. Okay? Which implies a new pair of divisors of a minus a prime. Okay? So now what I'm interested in is collecting up all the possible divisors of this guy here. because I look at the divisors of this and I grab two of them. The two divisors of that could potentially be two guys like this, okay? But the point is, anytime I have a b, it produces two divisors here, okay? So if I look at all the divisors, any pair of them, the collection of pairs of them is at least as large as the number of common neighbors. Every common neighbor produces two divisible pairs that divide into a minus a prime. So if I take all of them, I'm counting even more, right? Okay, so number common neighbors of a and a prime is less than or equal to, potentially much less, but less than or equal to, number divisors, not just number of divisors, number of pairs of divisors, right? Which is definitely a bigger quantity. So number of pairs of divisors of a minus a prime. Okay, so I want to predict that. I want to predict the number of pairs of divisors. Now that actually requires a little bit of number theory, so I'm going to have to state an observation here up at the top that will help us. Let me erase this for a moment. This is so much harder to erase than the ordinary whiteboard, but nonetheless. Okay, so what's known is, in general, the number of divisors of a number is small compared to that number, at least if the thing is large enough. So what I'm going to say is known. We're not going to prove this. This is a number theory fact. That for every delta, if I fix some delta greater than 0, there is x large enough such that number of divisors of x, which, by the way, I'm just going to write as equal to d of x for now. That's not the degree, it's the number of divisors. I know it's a little annoying notation here. It can be written as little o of x to the delta. Okay, so no matter what exponent I pick, so if I want to have few divisors, I want like less than x to the 0.001 divisors of x, right? If I pick 0.001 here, I can have that as long as x is large enough. So for x large enough and beyond, this function is an upper estimate, or an estimate. Let's put upper estimate. Yeah, let's write it as little as, okay? It's an estimate for the number of divisors. This being very small compared to x, as small as you like. You just might have to start later on for this to start being true, okay? So what that means, though, is if we come back down here, the number of common neighbors of a and a prime is at most the number of pairs of divisors of these two guys here, okay? So what's the number of pairs of divisors of this? Well, it can be written as, let me move it up over here, or I'll put it here first. So it's at most the number of divisors of a minus a prime, but squared, right? Because number of pairs, that's the total number of divisors. Squaring it certainly gives an upper bound on the number of pairs of divisors that you can pick for that guy there, okay? So now we have an estimate on the number of common neighbors of those guys, and it's this quantity here, okay? But by this theorem here, I can pick an epsilon to make this basically as small as I want compared to a minus a, okay? I want a minus a, though, in terms of n, okay? So how big is a minus a? Well, let me add it up here. Observe that a minus a prime is certainly at most n squared, right? All the numbers that are inside of my set A that I started with here have no reason to be larger than n squared, because the largest number in the sum set that I care about is n squared here. So if, there's no reason for anything to go beyond that. Frankly, nothing even really needs to be equal to n squared, because it's the sums that need to go up to n squared. But furthermore, the difference definitely is at most n squared, right? The biggest it could be is n squared, and then the smallest that could be is 1 or 0 if you like. And so you get n squared there, okay? All right, so I know that it's at most this, so what I can say then is there exists an epsilon greater than 0 such that the number of divisors of a minus a prime squared can be made to be little o of n to the 3 times epsilon. Okay, so I'm fooling around a little bit here. This 3 isn't really necessary, right? Because I can make d a minus a, d of x, I can make that x to whatever I want there. So a minus a, I can inside of that to the epsilon. And this is at most n squared, so I have at most n squared to the epsilon. And I actually even overestimated more by putting a 3 instead of a 2. But even I could make the 3 disappear by making epsilon even smaller. I leave this here for computational reasons. It's just nicer at the end here. Okay. So the point being, though, the number of divisors of a minus a squared, excuse me, a minus a prime, quantity squared, is a little o n to the 3 epsilon. All right. And now just a little more erasing, and I'll be done with the proof here. Okay, so I want to continue what's going on down here. I'm going to use this fact in just a moment, so let me leave that up here. But now I know I have a bound on the number of common neighbors. A bound on the number of common neighbors of 2 vertices A and B. So what does that mean? It means for any 2 vertices, right? This holds for any, A and B are arbitrary. Certainly any A and B satisfy this guy here. Right? So what does it mean? It means any 2 vertices have at most, I'm going to call it T, which is just equal to n to the 3 epsilon neighbors, common neighbors. At most that many common neighbors. Okay, I'm hiding the n inside the t here just for a moment, just so it's easier to see what theorem I'm going to apply. So what does that mean? If I take 2 vertices, any 2, and look at their common neighbors, right? So these are common neighbors of these 2 vertices. There's less than t of them. Okay, so what does that mean? That means that my graph is k2t free, right? That's exactly what giving a bound on the size of a common neighborhood is. It's saying you don't have a k2t, right? This is a complete bipartite graph. Their common neighbors goes to everything, and I have less than t. So I'm k2t free. Now, by Kuvary-Shosturán theorem, we have the following, that the number of edges in G is at most, well, what does Kuvary-Shosturán say? It says at most 1/2, t minus 1, you may have to look this up, raised to the 1/2, n to the 3/2, and then there's this plus error term in n. Okay? But what else do we know? We know from the observation that E of G is at least n, so put at least n there. Could be much bigger, but it's certainly at least n. And we also know that t minus 1, well, t is just n to the 3 epsilon, so I'm going to put n to the 3 epsilon in there, and I'm even going to drop the 1/2 there. So I'm just to write that this is at least, and I'm going to drop the error term there, because I increase that, it certainly works. So I have n to the 3 times epsilon times n to the 3/2. Okay? Now, what am I missing here? No, I made a mistake here. I made a mistake. This is not an n. This is not an n. This is the size of A, right? The graph's vertex set was the vertices of A. Okay, so A is here. Yes, A is here. I don't know the size of A. I'm trying to determine the size of A. Okay? I know that the number of common neighbors is little o of n to the 3 epsilon, so I put this instead, but I don't know the size of A. Okay, so now what I want to do is actually solve for A. And that's not in the notes, but maybe I'll go through it real quick here. Because normally with Kuvary-Shosturán we get a bound on the number of edges, which we did here, but I actually no longer care about the number of edges. I just care about solving this for A, because I want a bound on A, right? I'm looking for that bound on A. You may see it already, but let's finish the proof. So how do I finish the proof? Well, this n is at most this quantity here. So all I have to do is solve for A, okay? So what I'm going to take is the 2/3 root of both sides, right? Maybe I'll bring this guy over there first. I don't know what's the easiest here. Let's take n minus, n to the 1 minus 3 epsilon. That's what happens when I divide both sides by this guy. This is less than or equal to A to the 3/2. Okay? Now I'll take the square root of both sides and then the 3rd root of both sides. So what happens here? I get this A, and then, okay, I'm not going to get the exponent I was expecting, but 1 minus 3 epsilon, all raised to the 2/3. Okay, and what does this give me here? I've got n to the 2/3 minus 2 epsilon. Okay, so it's not I should have chosen this exponent a little more carefully earlier on, but it doesn't change anything. I can make epsilon as small as I want. So what does this imply? This implies that a is greater than or equal to n to the 2/3 minus 2 epsilon. Okay, which is what I got over here. Granted, that should have been, there's no 2 there. I can get rid of the 2 there if I go back over here and change this. I guess I went 3/2 epsilon as the exponent here. It'll work. I have complete control over epsilon. I can choose it to be anything I like. So frankly, I could just make the 3 disappear there if I wanted. And then I'd have over here over 3 epsilon. It's just kind of whichever form you prefer to see. Okay? But nonetheless, that ends the proof there. Okay? So just to look at it one more time really quickly here, I construct a graph A on graph G on the vertex set, whose vertex set is this guy there. I know that it has a few edges at least because of this bound here. Then I go and look at common neighborhoods, and they can't be too large because if they're too large, because they're bounded by the number of divisors of A minus A prime, right? That has something to do with the number of squares that are available there. So common neighborhoods are not too big, which means the graph is K2T free. So we can apply Quadratische to get an edge bound. And I don't care so much about the edge bound. I'm actually looking at an upper bound on n, which is this guy here. And then I just solve for a, which gives a lower bound on a of exactly what we wanted from the theorem. Okay.